Today's webinar featuring the journal paper, Automatic Detection of Ionospheric Scintillation-like GNSS Satellite Oscillator Anomaly using a machine learning algorithm, which was published in the fall 2020 issue of Navigation and was written by Yunshan Liu and Dr. Jade Morton. Today's webinar will be presented by Yunshan Liu, or Leo, and he's also joined today by Dr. Jade Morton. Yunshan Liu is a doctoral candidate in Ann and H.J. Smead Aerospace Engineering Sciences at the University of Colorado Boulder since 2017. He received a BE at the University of Electronic Science and Technology of China in 2013 and an ME degree from Nanyang Technological University, or NTU, in Singapore in 2015, both majoring in wireless communications. He worked on machine learning related problems as a research associate at NTU and later at the Rolls-Royce at NTU Corporate Lab until 2017. His current work focuses on applying machine learning techniques to GNSS-based remote sensing tasks. Dr. Jade Morton is an aerospace engineering professor at University of Colorado at Boulder. She received a PhD in electrical engineering from Penn State. Her research interests lie at the intersection of satellite navigation and remote sensing of the space environment, atmosphere, and Earth's surface. She is the current president of the Institute of Navigation and is a fellow of IEEE, ION, and the Royal Institute of Navigation. We greatly appreciate their time and the work that Mr. Liu and Dr. Morton have put into today's webinar. Following the presentation, they will both be available to answer questions. To ask a question, you can click on the Q&A box on the lower bar of your Zoom viewer and put your question in at any time. So thank you for joining us. We'll now turn the time over to Leo.
Okay, so thanks for the introduction by Rick. And first I want to check, can you hear me all right? Okay, so hello everyone and welcome to this ION webinar. And my name is Yunshan Liu and usually I go by Leo. I'm a PhD student from Satellite Navigation and Sensing Lab at the University of Colorado Boulder, known as SenseLab, supervised by Professor Jade Morton. And today, Professor Jade Morton and I will be sharing our work on satellite oscillator anomaly detection with you. So given such a long title, I would like to highlight a few words here. This work is about automatic detection of ionospheric scintillation-like GPS satellite oscillator anomaly using a machine learning algorithm. And here is the outline of today's presentation. I will start with motivation and objective, followed by the introduction of satellite oscillator anomaly detection, where I will talk about two methods we implemented. The first one we called SVM RBF-SVM, while the second one is random forest. And the detailed introduction of these two detection methods will be discussed. Then the performance evaluation and comparison will be conducted, followed by the satellite oscillator anomaly detection results and observations. And finally, we will conclude our work and show some future work. So the motivation for detecting satellite oscillator anomaly is that it affects all the users that rely on its signal integrity, especially for safety critical applications like aviation. So it is important to monitor its signal quality where the automatic detection is desired. So here, the objective is to conduct automatic satellite oscillator anomaly detection by using machine learning. This slide shows the oscillator anomaly detection procedure. In order to detect oscillator anomaly, we have to distinguish it from ionosphere scintillation and no disturbance. And here, scintillation refers to rapid phase fluctuation of the signal propagating through ionosphere. To conduct this detection task, phase measurements are first input to the machine learning-based oscillator anomaly detection, where two methods are developed, as we mentioned in the outline. First, SVM RBF-SVM, and second, random forest. In the next few slides, I will first talk about the feature engineering, followed by the introduction of these two methods. And the one thing I want to emphasize here is that the commonality between scintillation and oscillator anomaly is that both are phase disturbance, which will be considered in feature engineering. This slide talks about the first feature we applied, power spectral density, PSD. Here, feature engineering is a commonly used term in machine learning community which is the process of using domain knowledge to extract features from raw data. And later on, these extracted features will be used as the input to the machine learning algorithms. And given a segment of phase measurements, the power spectral density can be obtained and used as features. And the left plot shows examples of PSD for oscillator anomaly in blue, scintillation in orange, and no disturbance in green. And the no disturbance example shows low power density across all frequencies, while oscillator anomaly and scintillation show high power density at some frequency over here. So we can use this information to distinguish disturbed measurements from no disturbance. And here we use this entire PSD spectrum as well as the maximum value of the PSD as features. So once we can do this, the next step is to construct features that distinguish between scintillation and oscillator anomaly, where both are phase disturbance. And so let's come to this slide talks about the second feature, which we call ratio, that can be used to distinguish between oscillator anomaly and scintillation. The plot on the left shows an example of oscillator anomaly phase measurements. The phase measurements on L1 has the largest phase deviation, while L5 has the smallest. This is because the phase deviation caused by oscillator anomaly is proportional to carrier frequency. An example of scintillation is shown on the right. Here, L5 has the largest deviation, while L1 has the smallest. This is because the phase deviation caused by scintillation is inversely proportional to carrier frequency. So we can extract features that reflect this carrier dependence information to distinguish these two classes. So here is the scatter plot of GPS L1 phase deviation versus L2 phase deviation. Given that oscillator anomaly is proportional to carrier frequency, a scatter plot of oscillator anomaly example should lie on this black line, while for scintillation, it should follow this red line. So we plot two examples in last slide here, and obviously the oscillator anomaly example plot in black circles follow this black line, while the scintillation example in red crosses follow this red line. As a result, we can use phase measurements from two frequency bands and do a linear fit to find this slope, which we call ratio in this work. And by using this ratio, we can distinguish between scintillation and oscillator anomaly. So this is the second feature we proposed. And one thing I would like to emphasize here is that we introduced two types of features here: power spectral density, PSD, and ratio. And later on, both methods will use these two types of features to detect satellite oscillator anomaly. And this slide summarizes the feature engineering given the available frequency bands. Our work focuses on detecting anomalies on signals transmitted from GPS block 2RM and block 2F satellites. Features of PSD can be obtained from each available frequency band. For the ratios, dual frequency signal can only generate one ratio between L1 and L2, while triple frequency signal can generate three ratios. They are L1 versus L2, L1 versus L5, and L2 versus L5. And of course, triple frequency signal has an additional frequency band, which offers more information. And later on, a performance comparison between these two will be discussed. So from this slide, we start to introduce our first satellite oscillator anomaly detection method, which we call SVM RBF-SVM. And before showing you the detection diagram, I would like to first introduce the machine learning algorithm we used, support vector machine SVM. Here is an example illustrating how SVM works in feature domain, where you have two features in this example, feature number 1 and feature number 2. Samples from two classes are shown, blue circles and red triangles. Each sample has two features, feature X1 and number 2. And the purpose of SVM is to correctly classify these two classes by designing an optimal hyperplane in between that maximize the margin of these two classes, and as well as minimize the misclassification errors. So one important property of this SVM is the capability of applying kernel trick. Here, another example with two classes is shown on the left in the feature domain, red dots and the blue circles. In this data set, each sample has two features, x1 and x2. And it is clear that there is no way to design a decision boundary, which is a line in 2D, to correctly classify these two classes. However, if we apply a polynomial kernel to map these two-dimensional features, x1, x2, to three-dimensional features, x1, x2, and x1 times x2, it can be transformed to a linear separable problem shown on the right, where a plane shown in gray can successfully classify these two classes. This is the kernel trick in SVM, which maps the feature to a higher dimension where the problem is more probable to be linear separable. And to implement the SVM, a commonly used kernel is radial basis function kernel, aka RBF kernel. In theory, it maps the feature to infinite dimension, where this transformation could make the classification problem easier. And in this detection method, we will use this RBF kernel in one stage. So finally, this is the block diagram of SVM RBF-SVM. It involves three stages. Given the phase measurements from multiple frequency bands as input, stage 1 detects phase disturbance, where power spectral density PSD is used as features and input to a linear SVM classifier to conduct the detection. And once the disturbance is detected, we move on to stage 2 to distinguish oscillator anomaly from ionospheric scintillation, where ratios are used as features and input to a RBF-SVM to conduct the classification. Once the oscillator anomaly is detected over here, we move on to stage 3 to differentiate satellite oscillator anomaly from receiver oscillator anomaly. This is based on the fact that a receiver oscillator anomaly should simultaneously show up on measurements from multiple satellites in view, while a satellite oscillator anomaly is only present on the measurements from that particular satellite. So we can check if the same anomaly is observed from multiple satellites to identify whether it is a satellite oscillator anomaly. And no machine learning algorithm is required for this stage 3. Since this third stage is a trivial process, later on we will focus on performance evaluation of the first two stages, which is about this oscillator anomaly detection. And SVM RBF-SVM we developed has a few drawbacks. First, due to historical reasons, the first stage, phase disturbance detection stage, is inherited from a simulation detection method, and it has problems on detecting small oscillator anomalies, where a large number of small anomalies are missed in the first stage. And the second, the machine learning algorithms for the first two stages, the linear SVM and RBF-SVM, are independently trained and optimized, which may not be global optimal. As a result, an end-to-end framework on oscillator anomaly detection is desired. And that's the reason we developed the second detection method. We call it random forest. In this second detection method, the machine learning algorithm we apply in this method is random forest. And for simplicity, we abuse this term, random forest, and name this detection method also as random forest. And this slide shows the building block of random forest called decision tree. The left plot shows a data set in feature domain where each sample has two features, x1 and x2. Three classes are shown in the plot with label A, B, and C. And the black and the green dashed lines are the decision boundary of the trained decision tree. An illustration of this trained decision tree is shown on the right. The classification procedure of a decision tree is to traverse from roof to leaf and assign the leaf label to the data sample. So for example, we have a new data sample with feature x1 equals to 4 and the feature x2 equals to 3. First, x2 equals to 3 is larger than threshold 2. We move on to the left subtree. Then x1 equals to 4 is larger than threshold 2. We move on to the leftmost leaf. And now the label C is assigned to this sample. This is how a decision tree classifies a data sample. However, a single decision tree classifier, they may not achieve a very desired performance, so we apply random forest. Instead of using a single decision tree, Random forests utilize K decision trees, where each decision tree makes the classification independently. And eventually a majority vote is conducted, so random forest outputs the label with most votes. This is how random forest works. And this slide is the block diagram of the detection method named random forest, which is the second detection method we developed. Given the phase measurements as input, the first stage is to distinguish the oscillator anomaly from no disturbance and ionospheric simulation. And here features PSD and the ratios, they are concatenated together and extracted and input to the random forest to conduct the classification. And once oscillator anomaly is detected, we move on to stage 2 to differentiate satellite oscillator anomaly from receiver oscillator anomaly, where we can check if the same anomaly is observed from multiple satellites to identify whether it is a satellite oscillator anomaly. And the main difference compared to SVM, RBF, SVM is shown in this red box, where 2 stages on oscillator anomaly detection in SVM, RBF, SVM are simplified into only one single stage, where a 3-class classification problem is conducted. And later on, we will show a performance comparison between SVM, RBF, SVM, and the random forest. And to evaluate the performance and compare the performance, these slides talk about the dataset and evaluation method used for that. The data we used in this application is 100 Hz phase measurements. The phase measurements are divided into chunks, where each chunk is used as one sample in the dataset. Each chunk is 30 seconds long and classified independently. In order to train and test the method, we manually inspect a large amount of data and labeled more than 700 simulation samples, more than 200 oscillator anomaly samples, and more than 400 no disturbance samples. And for the purpose of evaluation, we randomly shuffle the data and use 90% for training and the rest for testing. And here is one of the main results, the performance comparison. Accuracy, false alarm rate, and F1 score are illustrated for both dual and triple frequency signals. Here, F1 score is defined as a harmonic mean of recall and precision, and is used to evaluate the performance of an imbalanced dataset, which is the case of this dataset. The last column is random forest, and second last column is SVM, RBF, SVM. The other 5 columns are machine learning algorithms used to compare against the random forest, where same features are used as input. A few observations can be obtained from this table. First, observation is that the method using triple frequency signals has better performance compared to the one using dual frequency signals because of the additional information offered by L5 band. And second, random forest achieves the best performance, outperforming SVM, RBF, SVM. This is because of the benefit from the end-to-end optimization we mentioned just now. And the third, random forest outputs other machine learning algorithms like logistic regression all the way to RBF, SVM. This explains why we switched to random forest for the second detection method. As a result, the random forest is the best choice to detect oscillator anomaly. And one thing we want to emphasize here is that 98.4 and 99% detection accuracies show that random forest achieves superior performance on not only oscillator anomaly, but also scintillation detection. And given the accurate detection method, we apply this random forest to our database to conduct automatic satellite oscillator anomaly detection. And SVM, RBF, SVM is also applied for the purpose of comparison. We process data from 5 stations located at different places: Alaska, Puerto Rico, Chile, Greenland, and South Korea. The date and the number of days available are shown for each station. And we process all the satellites from block 2RM in red and the block 2F in blue. And this slide shows the number of station-wise detected satellite oscillator anomalies. Number of detected events and average number per day are shown here. Immediately, we can observe that random forest detects way more number of events compared to SVM, RBF-SVM. This is because the inherited phase disturbance detection, as in SVM, RBF-SVM, missed a large number of small satellite oscillator anomalies. And given this table, I would like to ask a question to the audience where you can select your answer through the poll. The question is receiver oscillator anomaly versus satellite oscillator anomaly. Which one do you think occurs more frequently, and what do you think? We can take about like 30 seconds to think about it. Then we can show the poll answer and talk about it. Okay, Rick. So if it's enough statistics, we can show the results of the poll. Thanks. So there are like 76% thinks that receiver oscillator anomaly occurs more frequently, and that's our intuition. But the results I will be showing you with you is our observation, is shown here. This is what we observed from the processed data. In total, approximately 32,000 satellite oscillator anomaly events are detected through our algorithm, while only 370 receiver oscillator anomaly events are detected through our algorithm. And we process all the data, and this is the result we get. And let's move on to the next one, is that at this stage, you might wonder, are these events detected by random forest, more than 32,000, are genuine satellite oscillator anomalies? We were also concerned about such a large number of anomalies detected by random forest. So in order to verify these events, I randomly picked 200 anomalies events, and out of this 32,000, and conduct a manual inspection. And we found that 197 events are genuine anomalies, which correspond to a precision score of 98.5. And in performance evaluation, a precision score of 97.7 is obtained for random forest with dual frequency. So here is an example explains what precision score means. Suppose you have a precision score of 90%. It means that if the classifier detects 100 oscillator anomalies, 90 out of the 100 are genuine anomalies. And you might observe that these two values are very close to each other, indicating that random forest performs as expected. And before showing the next slide, I want to have one more question to the audience through the poll. And can you guess what is the typical magnitude of maximum phase deviation for a GPS satellite oscillator anomaly? Is it 0.01 cycles, 0.1 cycles, 1 cycle, or 10 cycles? Okay, let's take a look at the results. So about 41% think it's 0.1 cycles, and 36 think it's 0.01, and 23 think it's 1 cycle. And of course, it's quite hard to see like a 10 cycles, so it's 0%. That's reasonable. So the next slide will explain here. The answer is around 0.1 cycles over here. And this slide shows the comparison of histogram on L1 maximum phase deviation, where we extract the L1 maximum phase deviation for each detected event and plot a histogram. So this plot shows the distribution fit of the histogram obtained by these two methods. The distribution of random forest shifts to the left compared to SVM, RBF, SVM. This again shows that random forest can detect more small anomalies compared to SVM, RBF, SVM. and also answer our question, which is most of them will be around 0.1 cycles. And so from now on, I will only show the detection results using random forest because of the performance of random forest. In this slide, we show that there are events detected by random forest at different stations corresponding to the same satellite oscillator anomaly. This is based on the fact that if a satellite oscillator anomaly happens, it should show up on all receivers in view. For example, it may be simultaneously observed by stations at Alaska and Greenland if the satellite is in view for both stations when the anomaly happens. Remember that the classification we proposed is conducted independently for each chunk of measurement at each station. And in 2018, we detect approximately 30,000 events from these 4 stations. After post-processing, it turned out that there are more than 5,000 anomalies observed by 2 stations, corresponding to 2 times 5,385 detected events. And there are 1,085 anomalies observed by 3 stations, corresponding to 3 times 1,085 events. And surprisingly, there are 5 anomalies that are simultaneously observed by 4 stations, and we will show an example in the next slide. And in total, approximately 6,000 anomalies are observed by at least 2 stations, showing the effectiveness of random forest on satellite oscillator anomaly detection. This slide shows one example of the detected satellite oscillator anomaly from PRN10 observed by 4 stations on May 23, 2018. Again, I want to emphasize that these 4 events are detected independently. We found out they correspond to the same satellite oscillator anomaly by post-processing. At this time, satellite PRN10 is located above Pacific Ocean, close to US coast. Although different noise is presented, they all have the same shape of the anomaly. And in addition, all the peaks are observed at the same time, 6:39 a.m. UTC. And this observation shows that this is indeed a satellite oscillator anomaly. And before showing the next slide, I would like to ask one last question through the poll. On detecting all the satellite oscillator anomaly, which block of GPS satellites has the least number of oscillator anomalies? What do you think, block 2F or block 2RM? So let's take another 30 seconds to think about it. So let's take a look at the statistics of this question. So about like 45% thinks block 2RM should have least number of oscillator anomaly, while 55% think block 2F should have least. This is reasonable because block 2F is newer than block 2RM. It's supposed to having like a better clock. And let's see the results. So the short answer is that block 2F, from our observation, block 2F has more anomalies than block 2RM. And in this slide, we show the satellite-wise average number of detected events per visible day. And here, a visible day we define as a 24-hour period during which the corresponding satellite is in view with elevation above 20 degrees. And a few observations can be found from this plot. First, most anomalies are detected from block 2F satellites in blue. Second, not all block 2F satellites have large number of detected anomalies each day, for instance, PRN8 and 24. And this may be based on the fact that PRN8 and 24 use cesium clocks, while other satellites in block 2F use rubidium clocks. And more detailed investigation will be conducted in the future. And third, all block 2RM in red shows small number of detected anomalies each day. And finally, on average, we can observe like more than 35 events per day detected from PRN10 and Alaska. And after the station-wide statistics, we also want to know if the occurrence of anomaly is periodic or random. This plot shows the anomaly daily occurrence over Greenland for PRN1. Apparently, random occurrence pattern is observed, sometimes one anomaly each day, while other days show more than 5 anomalies each day. And the same observation can also be found from PRN10. On some days, we detect only 1 anomalies, while other days it sees like more than 10 anomalies. And finally, we want to conclude our work is that the both performance analysis as well as the detection statistics show the capability of random forest on automatic satellite oscillator anomaly detection. And the second, preliminary detection results show that different satellites have different behaviors. And finally, the accurate detection results show that the method not only detects oscillator anomaly, but also scintillation with very high accuracy. And in the future, our next step is to first design satellite oscillator anomaly detection methods for other constellations like Galileo, GLONASS, and Beidou. And second, apply this accurate detection methods on more data, such that global characterization of GPS satellite oscillator anomaly and scintillation will be conducted. And finally, I would like to acknowledge that the presented work is supported by Space Weather Technology Research and Education Center, SU Boulder, and a contract from Lockheed Martin. I would like also to thank Dr. Penny Axelrod for suggesting this research topic and providing guidance. And that's all we have. Thank you very much for listening. So let's check if we have any questions.
So Leo, thank you. You did a great job. I actually have been answering questions, but I haven't got a chance to answer Professor Todd Walter's question. He said, what is the largest satellite phase deviation that you have detected based on the processing you have done?
I think it's the anomaly that the reason we started this work, because at the very beginning we saw GPS solution papers talking about this large deviation of the satellite oscillator anomaly. It's about like 1.5 cycles. And from there, we start to design this machine learning algorithm. But most of the anomalies we see is around 0.1 cycles. But there are about like tens of anomalies. They are more than one cycle, but not exceeding 2.
Okay. I mean, for those people who are, I've already answered the question. If you didn't think it was clarified, we'll be happy to address them again. So the next question I haven't got a chance to answer is, you explained that you're using 100 Hertz phase measurement, but I missed the chunk explanation. Could you clarify if you're using all measurement or just the one measurement every 30 seconds to compute the phase deviation? That's a straightforward answer. Yeah, if you want to take it, Leo, feel free to. Oh yeah,
it's from the machine learning perspective, we treat each 30 seconds independently for the classification. But to compute the phase deviation, we detrain this entire chunk of data, and then we cut them into 30 seconds chunks and do the classification independently.
Yeah, so maybe more straightforward answer is that we use the 100 Hertz phase measurements and not every 30 seconds. But Leo have also evaluated if you use a low sampling rate, how would this performance change? So he went down to 10 Hertz, and there is slight degradation in the performance, for example, precision. And if it goes further down to 1 Hertz, the degradation is much more noticeable. So higher rate measurement is important to capture the kind of phase anomaly. So in the work that he presented here, these are all based on 100 Hertz, but we can do a low rate, just not too low. Yeah.
Okay, thanks for clarifying. I just realized I misunderstand the question. So in the 30 seconds chunk, we use all the measurements. It's like 3,000 samples, phase deviation, to compute the PSD, the power spectral density, as well as the ratio, as the features. Then we can input them into the classifier to determine whether it's an oscillator anomaly or not.
Yeah, and I think there's a question from Sergey, and his question is, how do you manage to measure oscillator anomalies so precisely when Carrier phase errors are on the order of 0.1 or 0.05 L1 cycles, is the Carrier phase accuracy limited for the method? And do you want to take that question?
Yeah, I do think that's the reason we start with this work with substantial receivers, because they are known to have low phase noise. Because you see most of the detected anomalies only about 0.1 cycles. So if your phase noise is above that, I don't think we are able to see any like anomalies from that extent. And one thing I want to mention is that the reason we can see 0.1 cycles anomaly is because we propose two features. One PSD and other is a ratio. So ratio is not about magnitude. Ratio is about the slope between different frequency bands. By using that information, it's very straightforward for the machine learning to tell, oh, this is the oscillator anomaly and this is not.
And also the power spectrum density itself can also help to bring the features out, because just because you have phase error, let's say at 0.1 cycles, but the substantial receiver has low phase noise because the oscillator had. But even if the detection level is similar to the phase noise, when you look at the power spectrum density, it captures different part of the energy coming from the phase. So, so that also allows us to go lower than actually the phase noise level, because we're looking at a certain part of the spectrum. Okay, there's another question now from Daniel. Did you train your classifier on those data you showed us in analysis section, or other data sets were used? Yeah, Leo, you can take that one.
Yeah, so as I mentioned in the data set, we manually inspect the data is included in the one I showed, but it's only about like 20 days of data. Then we extract some anomalies and train the classifier. And then we use this classifier to run through this entire like more than a year of data and detect all the events from there.
Yeah, so the quick answer is we actually trained the data from the information Leo had showed you in the analysis section, and but we applied the model trained using that data to other new data, and then Leo randomly picked the newly classified result, do additional manual inspection to make sure those are indeed oscillator anomalies, and that's why he got that 98 point, I remember, to some percentage precision. So the other question Daniel asked is, how did you remove normal ionosphere trend? That's, if you want to take it, Leo, you're welcome to.
Maybe Professor Morgan can help me on this.
All right. So yes, we use the detrending technique because we are understanding that the method originally started with a technique developed by Yu Zhao, who is actually in the audience today. And she had developed this SVM machine learning algorithm to detect ionospheric scintillation. In order to do that, we have to remove not only the ionosphere trend, the normal background ionosphere trend, we also have to remove other things, the troposphere trend, and the range, the geometry. So that's part of the detrending process. But that shouldn't be too critical because we understand those processes very well. They're relatively low frequency, so the filtering technology can really remove those well.
Mm-hmm.
I think that, okay, there's another one. High level impact question. Whoa. When these anomalies occur and are present in a received signal, say in the user GPS receiver on the Earth surface, what errors to the GPS users are experienced? Example, i.e. time acquisition error resulting in your location accuracy error increases or stuff like that. Well, that actually, I think, is related to what Professor Todd Waters' question. So it depends on how large is oscillator anomaly magnitude is. If the oscillator anomaly magnitude is very large, your receiver may have a cycle slip. And if it's outside of the polling range, because you notice that some of the example Leo showed, those anomalies are very abrupt. So if it's really abrupt, you may lose log. So that could be some of the impact. But most of the oscillator anomalies that Leo was able to detect are relatively small in magnitude. If that is the case, it's, you might even argue, would that really impact the accuracy of the navigation solution that much? Maybe not. And I understand one of the reviews of our paper said, if you have such a small anomaly, why should we bother with it? And my counter argument is this: if people don't care about anomalies that happened in 0.1 cycles of the Curie magnitude, why would this entire community spending so much money developing precision clocks for satellites? So there must be other reasons for that as well. I think, the performance of the clock itself is a high impact factor in navigation solutions. So I don't know if that answered your question or not.
And I also see another question from Manish just early on. I'm not sure Professor Morton asked it already. The question is, can you show some statistics on false alarms when using random forest? That's a very good question. So false alarm is that you have to know about the false alarm is that you detect a oscillator anomaly, but actually it's not. Versus all the normal situation, which is no disturbance or scintillation. So we have to have like a ground truth of that, and it's very hard because I have to manually inspect all the events and make sure there are indeed no disturbance and scintillation. Then we can show the false alarm rate. The reason we show precision to make sure that our algorithm works as expected is precision is actually just you detect 100. You just want to check what's the percentage are genuine satellite oscillator anomaly, and it's a very easy metric to check. That's why we chose that.
Okay, so this is related to statistical models. Could one use ionosphere-free and geometry-free combinations to isolate anomalies and scintillation from each other, then apply either statistical method or simplified classifier? I think Yu Jiao Joy, who is one of my PhD students, she asked a similar question before. Leo, you can take that. Yeah. It's basically the same. If you already know these ratios, couldn't you just use? Yeah.
This is a perfect question. So when I showed these two ratios, you can see it's very easy. So actually, at the very beginning, we thought we didn't need any machine learning, just use a threshold. And if it's larger, it's scintillation. If it's lower, it's like larger than 1, the ratio is scintillation. Otherwise, it's oscillator anomaly. Then we saw the performance is around, like accuracy is around 80%. The reason is that scintillation, they are not only sometimes like refraction, and sometimes diffraction will be introduced. So the phase noise and the fluctuation is like more random. And in that case, and it's noisier. And when you compare the ratio, it won't like actually perfectly align with that line I just showed you as an illustration. And in that case, that's the reason we want to introduce machine learning in this scenario. Is we want the data to tell us the story and try to use the data to say, oh, we want to design this kind of like a curly decision boundary instead of like a simple threshold, then we can achieve a better performance. That's the main reason we chose to use machine learning. And if you refer to our first paper about the SVM RBF-SVM, we actually compared the machine learning algorithm to this simple threshold method, and we saw performance improvement.
Yeah. So the key to the answer is, even though Leo have showed you example to show that the ratio is good identifier, but that is not always true, because for ionospheric scintillation is a rather complex phenomena. So it all depends on your signal propagation direction and the kind of plasma disturbance you have, how fast it is moving, how thick it is, and how many different layers there are. So that ratio actually could vary. And so a simplified statistical model or classifier, you can do it, but you won't do as a good job as what Leo is presenting to you. These are all good questions. Okay, I think there are a couple more coming up. The random forest is a supervised one. However, it is better to consider unsupervised learning since we don't know whether the available data includes anomaly or not.
Let me see how I can answer this. Is that from my understanding, most of the time we want to pursue unsupervised learning is because we don't have the labeled data such that we can train a supervised classifier. Because usually supervised classifier has better performance because you inject the label information into it. And since in our case, as I just presented, we spend a lot of time just manually inspect a lot of events and found about like a data set with more than 1,000 samples with 3 classes, the anomaly and the simulation and the no disturbance. In this case, we can just pursue the supervised one and train it. And as you can see from the performance evaluation, it's very good. Then in the future, we can just apply this supervised machine learning algorithm to other like new data and just try to detect more satellite oscillator anomaly.
All right, I think there's one last question here from Daniel. So can this research be used to improve GNSS integrity? I think that's absolutely yes. Yeah, I would say it's one of the motivations behind this. Although we stumbled into this project by accident because Professor Penny Axelrod said, somebody said scintillation really aren't scintillation there due to oscillator anomaly, his paper went. And so that's how we started looking into it. Now looking back, I think, the method, especially random forest, it will classify oscillator anomaly against ionospheric scintillation. And in fact, we have another student working on a follow-up project that also classify against interference, IFI interference and multipass as well. So absolutely, yeah, we hope this research could help to improve the GNSS integrity.
And I see one more question from James. The question is, did you try other classification techniques such as principal component analysis? This is a very good question, which can link to the supervised versus unsupervised algorithms. Because this principal component analysis, PCA, is actually an unsupervised method. And all the machine learning we proposed, we developed over here is supervised learning where we can inject the label information. And we didn't compare that with PCA because I expect we can see like a very large performance gap between PCA and to our algorithm.
I don't see any other questions. I do have a meeting in 10 minutes. So Leo, thank you again for doing a great job. I'm gonna let Rick or Ken take over.
Okay, thanks.
Yeah, thank you, Leo, and thank you, Jade, both of you for your time today and for leading this webinar for us and sharing your research. Again, this paper is available for download on the ION website at ion.org. We've posted the link in the chat, and it will also be sent later by email. You'll find it on our website, again, at ion.org. If you go to technical content, look under webinars, you'll find the video for today, a copy of the slides, and a link to download the paper at no charge. Again, we thank you for joining us. Please be safe, and we look forward to seeing you at our next webinar in January.
Thank you.